Well, hello, everybody. It's a real pleasure to be here. Sorry, I don't speak Spanish, but I know it's very tiring to listen to somebody in a foreign language, but I'll do my best anyway. So my topic today is machine learning, finance applications, and key challenges. You may be thinking, John Hull, surely John Hull's in derivatives. What's he talking about machine learning for? And let me just explain a little bit about that. A few years ago, I guess it was about 5 or 6 years ago, I sort of switched my focus a little bit as far as both teaching and research is concerned. And I switched it from derivatives to machine learning. It wasn't a total switch, as you'll see, but there were a couple of reasons for it. I mean, one, I could see that machine learning was becoming more and more important, both from the point of view of research in finance generally and research in derivatives, and also is becoming really important to my students as well. They really needed to know about, I mean, they didn't have to be data science experts, but they really had to know about machine learning in order to, do well on the job market and survive. So I switched. All of my teaching and all of my research these days is in machine learning. Some of it is to do with machine learning and derivatives, as you'll see, but it's been a bit of a change of focus. As it says here, I've even written a book, Machine Learning in Business, because what I found when I was teaching this material is that most machine learning books are written by computer scientists for computer scientists. And what my students needed was a book which introduces them to machine learning and allows them to work productively with data scientists, but they weren't actually, I mean, some of them do actually become data scientists, which is kind of nice, but most of them don't. But they do nevertheless have to communicate with data scientists, understand what data scientists do. And that's what my course and that's what my book is all about. So let me start. I'm sure most people these days know what machine learning is, but just for completeness, what is machine learning? It's a branch of artificial intelligence. And the idea is that we give a computer program access to lots of data, much more data than we've traditionally used in statistics. And we let the computer program learn about the relationships between variables and make predictions. Okay, so it's just learn from large volumes of data. Some of the techniques have been around for a long time, as it says here, since the 1950s, but we couldn't really use the tools or techniques before because computers just weren't fast enough. So, and also data storage costs were quite high. But the reason why you've heard so much about machine learning in the last few years is not because all the tools of machine learning have been developed in the last few years. It's because computers have got faster and the tools that were developed quite some time ago have suddenly become feasible because, as I say, computers are now fast enough. I think it's important to distinguish machine learning from automation. This is really distinguishing the third industrial revolution from the fourth industrial revolution. So, I mean, we're all very familiar with the third industrial revolution. Third industrial revolution is about digitization, automating business decisions. I've given some examples here: payroll, sending out invoices, summarizing sales by region, that sort of thing. There's many applications of digitization. Machine learning is what we call the fourth industrial revolution, which is where, as I said earlier, computers are being used to create intelligence from large volumes of data. Now, I'm probably older than practically everybody who's listening, if not everybody who's listening to this presentation. I lived through the third industrial revolution in the 1970s and 1980s. Computers were just coming to be used. We had things like punch cards and paper tape and that sort of thing. And it was interesting. Some people really wanted to understand computers and learn how to use computers, and other people, as it were, put their head in the sand, as we say, and decided it was all going to go away. And of course, people who got on well in business were the people who learned how to use computers. They didn't have to become computer programmers, but they had to learn how to use computers to help make, business run smoothly. So I would argue that was the third industrial revolution. I would argue that as far as the fourth industrial revolution is concerned, which is, as I say, using large data sets and allowing computers to learn from large data sets, that is going to be just as important for business. This is what I tell my students, that it's really important to learn what machine learning is all about. And there's the language of machine learning, the tools of machine learning. You don't have to become a data scientist, but you have to know enough about data science to be able to communicate with data scientists. The analogy I draw, which I think is, some of my colleagues like this analogy, some don't like it, but the analogy I draw is with accounting. Because why do we teach our students accounting? We don't teach them accounting so they can become accountants. Some of them do, just a very small number, but they have to be able to interact with accountants. They have to be able to understand the language of accountants. They have to understand the product that accountants produce. And they have to understand enough about what accountants do to be able to work productively with accountants. And it's exactly the same thing as far as data science is concerned. So we teach data science for the same reason as we teach accounting. Okay, here's an example to illustrate this difference between the third industrial revolution and the fourth industrial revolution. And I'm going to use as my example something which is somewhere where machine learning's really had a very big impact, which is in credit decisions. A little bit of, okay. Seems to be a little bit of an echo here, but never mind. So let's suppose that you are working for an organization and the rules that loan officers use has been written down. So they're known rules, and all they're doing is applying those known rules and deciding whether to accept or reject loan applications. Then we could automate what they do, and that would be the third industrial revolution. Okay, that would just be digitization, the automation of something which, which is a sort of fairly standard activity requiring very little judgment. But the second and third bullet point here give a couple of applications of where we can use the fourth industrial revolution. And in fact, we do use the fourth industrial revolution in loan applications. First of all, let's suppose we didn't know what the rules were. But we know, obviously they must be using rules. It might be based a bit on their experience and that sort of thing. How do we determine the rules? The answer is we could collect lots of data on on decisions which were made about loan applications. So that data would be data describing the loan applicant. What's their income level? How old are they? Where do they live? How long have they lived in their present house? All those sorts of things. And we could collect that data and then collect data on the decision that was made. And what machine learning could do is relate the decision that was made to all of those aspects of the potential borrowers, people who have applied for loans. And those are called features. So that's one bit of terminology in machine learning. What we would call variables in statistics are called features. So things like, you know, the income level of the applicant, how long the applicants lived in their present house, all of that sort of thing are features which the credit officer will use in making a decision. So what, in that middle bullet point, what machine learning is doing is relating the features to the decision so that we can then go and automate the decision if we want to. The third one, though, is where the third bullet point is where we go one step further. And we can use machine learning to actually improve, potentially anyway, improve on the rules for accepting or rejecting loans, which is, it'd be a different sort of data that we would collect then, because then we'd have to collect data on how the loans actually worked out. Accepted a certain loan, what actually happened? Did the borrower pay in full or did the borrower default? Is there some way we could have predicted the loans which were going to default better than we're doing at the moment? So that's the fourth industrial revolution, another application of the fourth industrial revolution. One point I'd make, though, about that third bullet point is we've only got data on the loans that we actually made. In terms of whether the loans worked out well or not, we've only got data on the loans that we actually made. We don't have data on the loans that we didn't make, the applicants that we rejected. And so that's a potential source of bias, which maybe we'll come back to. So some people say, well, we've been doing this for a long time. This is just statistics. I learned about this when I was at university. But there is a difference. I mean, we could say that machine learning is kind of the new world of statistics, but there is a difference between the sort of the whole way in which machine learning operates versus the way traditional statistics operates. Traditional statistics, what you're told in statistics is the first thing you've got to do is to develop a hypothesis. And you're not supposed to look at any data when you develop that hypothesis. You're supposed to sit back in a comfortable chair and think, you know, I wonder if there's this relationship between this variable and that variable. Then once you've developed and refined your hypothesis, you collect the data and then you test the hypothesis. Excuse me. So that's how traditional statistics works. In machine learning, there's no hypothesis. What you do is you just go out and collect lots of data, and then you try different models to reflect that data, see which model fits the data best, and then you go on from that to either find patterns in the data or you make predictions. So, as I say, there's no hypothesis. It's just a case of collecting data and then finding the best model to fit the data. So we're going to talk about, well, there's three main categories of machine learning models, and we'll say a little bit about each one. Unsupervised learning. Unsupervised learning is where you're just trying to find patterns in the data. Okay, you're not trying to predict anything with unsupervised learning. You're just trying to say, you know, maybe you've got lots of customers out there and you want to understand your customers better. Unsupervised learning would be a good tool to do that, because you could say, well, if you're a bank, I've got, you know, customers who may be in the market for a mortgage, other customers who may be in a wealth market for wealth management services and car loans and that sort of thing. So by clustering or finding patterns in your customers, you understand them better. Supervised learning is where you are trying to predict something. And there's actually two sorts of predictions in supervised learning. You can either be trying to predict the numerical value of something. You know, for example, house prices in Toronto. You could develop a supervised learning model to predict house prices in Toronto from certain features of those houses. Or the other is classification, and I've already given an example of classification, deciding whether a loan should be accepted or rejected. That is, you're classifying the loans into two categories: accept, reject, and that's another application of supervised learning. And then there's reinforcement learning, which is where you're taking a series of decisions. You're not just taking one decision or one prediction, and it's a way of coming up with a good strategy for making a series of decisions in a changing environment. Okay, you can already see that the terminology is something you've got to get used to in machine learning. Excuse me. You know, why is it called unsupervised learning and supervised learning? It's a good question. It's not the terminology I would choose, but, you know, the idea is that if all you're trying to do is to find patterns in your data, you don't really have to supervise what the algorithm is doing too much. You just let the algorithm go. Whereas if you're trying to predict a particular thing, then you've got to supervise the algorithm to make sure it does the prediction properly. So that's, I think, where those two bits of terminology come from. Then there's reinforcement learning, which actually, because reinforcement learning is kind of a trial and error type of activity. You know, you try a particular strategy, see how well it works. If it works well, that reinforces that might be a good strategy. If it doesn't work out well, it reinforces that it's probably not a good strategy. So that's where reinforcement learning comes in. So unfortunately, you know, data scientists probably aren't going to change the way they talk about the different tools. So there's one of the things that, you know, to be able to work productively with data scientists, you have to do is to learn a bit about the terminology. And as I say, again, I like the analogy with accounting, because you do have to learn some accounting terminology in order to work productively with accountants. Okay, let's talk a bit more now about unsupervised learning. And here's, you know, a few examples of the applications. One, which I've already mentioned, you could cluster your customers to try and understand them better. So you've got, you know, lots of features of your customers. I mean, if you're a bank, for example, you've got features like, you know, what's the average account balance? How long have they been a customer with the bank? What other services of the bank do they use? And that sort of thing. And you can use unsupervised learning to understand your customers better, maybe communicate with them better. Because you know that customers that are in a particular category are more likely to want a particular type of service from the bank versus customers in another category. You may say, well, the marketing guys can do all that. But it turns out that actually unsupervised learning can be a powerful tool to supplement what, you know, the marketing guys do. Clustering countries for international investment. I'm going to talk about that in a minute, because that's a case study that I've developed that I use with students for this. And anomaly detection, if, you know, if a customer doesn't fall into a particular category, that might be an indication that there's something you want to know about that customer, there's some anomaly. So here's some results for this case study that I developed for students. It's what I did was I collected data on 121 countries. And that's a small data set as machine learning goes, but this is a first data set that I get my students to use, gets them into into using data sets and machine learning. They can play around with the data. So the three features the students end up using are the Peace Index, which is something provided by the Institute for Economics and Peace. So that's one feature of a country. The Legal Risk Index from the Property Rights Association. So that's a feature telling you how easy it is to if you've got a contract, to enforce your contracts in a particular country. And the third one is the GDP growth rate, the real GDP growth rate. So those are three things. If you're thinking about investing in a country, you might be interested in the Peace Index, the Legal Risk Index, and the real GDP growth rate. One of the problems is, of course, those are all on different scales. They might be on a scale from 0 to 100 or 0 to 10. And the real GDP growth rate, that could be, 0% or to 5%, something like that. So this is something that applies to most of the machine learning algorithms one comes across. You actually have to scale the feature values to make them comparable to each other, because, as I say, they're all measured on different scales. So what I did in this case was I scaled them so that they have a mean of 0 and a standard deviation of 1. Okay, so all of the features after scaling, as I say, I've got this mean of 0 and a standard deviation of 1. And you can see on the right-hand side here what this clustering algorithm came up with. So you've got, now I looked for 3 clusters in this. I asked the students to play around, actually looking at different features and different numbers of clusters. But this shows examples of what we get with 3 clusters. And I label the clusters because, of course, the algorithm doesn't know anything about how to label the clusters. So I've labeled one of the clusters the high-risk countries, the moderate-risk countries, and the low-risk countries. And you can see the high-risk countries, they've got a pretty low Peace Index. The Peace Index is 1.35 standard deviations below the mean on average. Okay. This is where the center of the high-risk countries are. The Peace Index, 1.35 standard deviations below the mean. The legal risk on average is 0.83 standard deviations below the mean. And the real GDP growth rate is 1.11 standard deviations below the mean. So clearly, the high-risk countries don't look too good on each of the 3 measures. The moderate risk countries, little bit below average on the Peace Index, a little bit below average on the Legal Risk Index, but actually do quite well on GDP growth rate, actually. Whereas the low-risk countries have good Peace Index, good Legal Risk Index, actually slightly below average on the GDP growth rate. Anyway, that clearly gives, some information that you can talk about, and may help you understand the different alternatives that are out there for international investment, if you want to. So that, I just give that as an illustration of the sort of thing that you do in unsupervised learning. You find clusters, but there's many different ways of doing it. Probably the most common, most popular algorithm is the k-means algorithm, but there are several others as well. So let's talk about supervised learning now. Supervised learning, as I said earlier, there's 2 categories of models. There's predicting the value of a variable, and there's classifying observations. And one point that's important to me is that when you're making predictions, you've got to be careful not to say, well, here's my data. This model fits the data really well. I'm going to use this model for predictions. You've got to test your model, what's called out of sample, which in good practice for supervised learning is that you divide your data into 3 sets: a training set, a validation set, and a test set. The training set is used to fit different models to your data, because remember, machine learning is about fitting different models and finding which one's best. So you fit different models to your data, and then you may want to see how well the model works, or generalizes, I should say, to a new data set, which is your validation set. So you might have the training set might be 60% of your data, and then the validation set could be another 20% of your data. And so when you've chosen, you said, this model looks really good, let's see how well it generalizes to the validation set. Well, it doesn't generalize at all well, maybe we should try this other model. But, that's how it goes. And then the test set is held back because the test set provides a final out-of-sample indication of how well the chosen model works. So, this is a little example that I use. This is predicting salaries from age in a certain profession. And the left-hand chart would be overfitting. You get a really good fit to your training set, but it doesn't generalize well. The second one would be actually underfitting, because just using a straight line fit, which doesn't capture the fact that, as a person's age increases, salaries tend to level off. And the best model is the one on the right. So that's the sort of thing you might start with this model saying fits the data really well, but you would find that model doesn't generalize well. So what you're looking for is a model that generalizes well, but has the least error. And this illustrates the sort of typical process you go through. There's some measure of model complexity, because you're in this particular example here, it's we're using polynomials. It's the degree of the polynomial, but there can be other measures of model complexity. And you have your training set and your validation set. And as you increase model complexity, the validation set tends to do almost as well as the training set up to a certain point. And then the model no longer generalizes well, and things get steadily worse for the validation set. Okay, so what you find in machine learning is you increase model complexity up to a certain point, denoted it by X here. But then you want to stop, because if you go any further in terms of model complexity, then the model no longer generalizes well, and actually things get worse for the validation set. Statisticians are pretty familiar with all of this. They call it testing a model out of sample. So what I want to run through fairly quickly now is a number of different prediction tools that we have in machine learning. And everybody's familiar with linear regression. So linear regression isn't really a machine learning tool, but what machine learning has done is introduce special procedures. They're known as things like ridge regression and lasso regression, to simplify the model and handle correlations. Because if you've taken a course in statistics, you are probably told that the independent variables, that's the x's here, they have to be more or less independent of each other. And that's, of course, rarely true. I mean, if you're predicting house prices in a city like Toronto, you're going to have things like what's the square foot of the living space, how many bedrooms have you got, how many bathrooms have you got, those sort of things, and those are all going to be fairly highly correlated. There's certainly, and as I say, we've got special tools in machine learning for handling the correlations and simplifying the model so that we get rid of the features, as they're called, or the independent variables that are not that important. We've got logistic regression, which is another well-established statistical technique for categorizing into category A or category B. Should we make this loan? Should we not make this loan? Again, we can use Ridge and Lasso to augment what logistic regression does. K-nearest neighbors is another tool which is actually a pretty intuitive tool, because what we do is we say we've got all this data and we have to, which, let's suppose again we're predicting house prices. We've got lots of data on house prices and the features of those houses. And then we have a new house that comes along and we ask, well, which houses is this new house most similar to? Which is probably what a real estate agent would do. And then you say, well, okay, it's most similar to these other three houses that we know the price of, so maybe we'll just average the prices of those three houses. And we can do a similar thing for situations where we're categorizing. So the methods we've been talking about so far have sort of said we've got all these features we want to predict from. We consider them all together. We, as it were, put them all in a box together. And, that's certainly what linear regression, logistic regression, and the k-nearest neighbors algorithm does. Decision trees are different, because what decision trees do is consider features one by one. And there are methods for doing this. So you first consider the feature with the most information content. And then you consider the feature with the next most information content, and so on. So here's, an example that, I use to illustrate this. It's data from this company, Lending Club, that was, or at least used to be, a peer-to-peer lender. And nicely, it provided all its data, made all its data public, which was kind of nice because we could do lots of analysis on it. So this is a tree that we develop from the Lending Club data. So we look at DTI, which is debt to income ratio. It's the percentage of your income that you use to service debt. And that seems to be the most important feature. So we put that at the top of the tree and we ask, is it greater than or less than 19.85? And then the next most important feature is your credit score, which is FICO in the US. And we ask, if you go down this branch of the tree, you ask whether FICO is greater than or less than 722.5. If you go down the other branch, it turns out the critical value you're interested in is 687.5. And so on. And there's, other things. You look at the person's income, you can look at whether they own their own home and that sort of thing. And what we have in the ovals at the bottom of the tree is the percentage chance that the borrower will totally repay the loan. So you go down the tree and at the end of the tree, you get, so for example, if you wind up here, there's only a 71.7% chance that the loan will be fully paid. Okay, another tool that is used is support vector machines, which is where you're trying to find a barrier in, so you've got certain number of features, say you've got 10 features, then you want to find a barrier in 10-dimensional space that separates the observations into the two groups. So, I mean, if you know, this is for situations where you're trying to categorize, come up with a couple of categories, and as I say, one method, particularly useful when you've got lots and lots of features, it turns out, you can come up with this barrier in dimensional space. Another interesting name, support vector machines. It's abbreviated SVM. Then you've probably heard about neural networks. Neural networks, you could regard neural networks as kind of an extension of linear regression. It's capable of finding any nonlinear relation for predicting a value or a classification. And here's a picture of how neural networks work. You've got your features, your inputs, which are on the left-hand side here, and you've got your outputs, which are things you're trying to predict, which very often you're only trying to predict one thing. So very often there's only one thing on the right-hand side here. And what we normally do, if we've got a regression model or something like that, is we try and relate the outputs to the inputs directly. In a neural network, we go through a number of stages. We have a number of layers, as they're called, hidden layers. And so what we do is we predict the value. We calculate the values in the first hidden layer from the values in the input layer, which are the features. And then we have the values in the second hidden layer from the values in the first hidden layer, and so on. So what we're really doing is we're breaking the relationship between the thing we're trying to predict, which is called the output layer, and the features we have, which are the input layer. We're breaking it into a number of, different subsets, as it were, or a number of different stages. And you might have 6 different stages in predicting the output from the input. Well, I'm running out of time, but I'd like to say a little bit about reinforcement learning. Actually, reinforcement learning is my favorite machine learning tool. I've used it a lot in the sort of research that I do. And what it is, it's a trial and error approach to coming up with a strategy for taking a series of decisions. Here's some examples of applications of reinforcement learning. Been very successful at playing board games, excuse me, such as Go and chess. You may have heard of this chess playing program AlphaZero, which was developed by a subsidiary of Google. AlphaZero is way better than the best human chess player, best human chess player, Magnus Carlsen, has got a chess rating of about 2,800. AlphaZero has got a chess rating of about 3,800. So much, much better. How did AlphaZero become so much better than the best human chess player? The answer is it played against itself millions and millions of times and just learnt good strategies. And that's the essence of reinforcement learning. You get lots, if a particular move works out well, reinforces that in this type of position, you should make this type of move. If it doesn't work out so well, then, we don't want to do that. It's been used in healthcare. Doctors very often have to make a sequence of decisions. So, you've got some problem, they try this, it leads to such and such a result, they try something else, and so on. And there's lots of data on, this, and reinforcement learning is proving to be very useful in terms of coming up with optimal strategies for sequential healthcare decisions. In finance, optimally selling a large block of shares, or in fact buying a large block of shares. The problem here is that you don't want to do it all at once because you'll move the market. So the question is, what should be your optimal strategy for buying or selling a large block of shares? You suppose you're selling, you sell some, you see what happens in the market, you sell some more, and so on. And so it turns out, reinforcement learning is an ideal tool for working out an optimal strategy for doing that. Portfolio management. I mean, if you think about portfolio management, that's a sequential decision process. You take a certain decision on your portfolio today, the world changes, you take another decision, you rebalance your portfolio tomorrow, world changes again, and so on. And in fact, hedging a derivatives portfolio is what I have used reinforcement learning quite a bit for. You've got a derivatives portfolio, it's evolving in a certain way. What's the optimal strategy for hedging it? And this, which I'm going to skip over this slide, but this is a description of some recent research that I've been involved in. You can, see the paper that underlies this research on my website, but basically, we look at how gamma and vega should be hedged. It's generally pretty expensive to hedge gamma and vega. Delta is relatively inexpensive to hedge, but gamma and vega are a lot more expensive. So what should be a strategy for hedging gamma and vega? That's the essence of this research. So this is my last slide. Machine learning is an exciting area. There's, lots of issues to be sorted out. Explainability is a big thing. I mean, some machine learning models are black boxes, and really the model is only going to be useful in business if it can be explained. And there's two aspects of explainability. You've got to be able to explain it to your employees who are going to use the model, but also to your customers. If you've got a model for deciding whether somebody should get a loan or not, you don't want to. You want to be able to, when the customer gets refused for a loan, you want to be able to give an understandable reason why they've been refused. And machine learning people didn't used to think explainability was important, but they do now. We have to also be concerned about biases. There's all sorts of potential biases that we want to avoid in machine learning, biases associated with gender and race and that sort of thing. And we also have to be careful. It's not just not including those as features, but not including other variables which are highly correlated with things like gender and race. I've mentioned how important it is, in my opinion, for managers to understand enough about the tools to work productively with data scientists and the analogy with accounting. And it'll be interesting to see how it evolves. I mean, a lot of people talk about, will we be able to maintain complete control of the intelligence we're creating? Will machine learning models sort of overtake? Certainly machine learning models can be more intelligent in some respects than human beings. How will we manage that? It'll be interesting to see. Anyway, thank you very much for listening to me. I'd be very happy to take any questions you've got.
Is not a chance that your keynote has been the opening note of the Risk Management Training Conference for most of its editions. We have some questions for you, sir. You have mentioned that learning about big data and machine learning for the fourth industrial revolution is going to be just as important as learning to use a computer was for the third industrial revolution. Which do you think is more difficult?
Sorry, I missed the middle part of that question.
Okay, no, don't worry, I'll repeat it again. You mentioned that learning about big data and machine learning for the fourth industrial revolution is going to be just as important as learning to use a computer previously. Which do you think is more difficult?
Well, that's a really good question. Which is more difficult? Is it more difficult to learn how to use a computer, or, the trouble is, now everybody knows how to use a computer. So we say, well, that's easy, it's intuitive, it's obvious. I think, but in the early days, which I lived through, of, punch cards and paper tape and that sort of thing, it was, it wasn't anything like as intuitive to use a computer as it is today. I mean, people have developed operating systems and that sort of thing to make it easy to use a computer. And I think the same thing is going to happen in machine learning. I think that, I've mentioned explainability, for example, and, I think that there'll be a lot of developments as far as making models more explainable and the tools more explainable. So I wouldn't like to say that it's going to be more difficult. It'll probably be about the same. But in the early days, and we are in the early days really of machine learning, it appears to be much more difficult because the user-friendly versions of the models have not really been developed yet.
Reinforcement learning requires lots of data. You mentioned that AlphaZero learns by playing against itself millions of times. Where do we get the necessary data for finance applications?
Well, that's very good. That's another very good question. And one way is to assume a model. So, those of you familiar with, with derivatives will know that a common model in derivatives is geometric Brownian motion, and then there are all other models where volatility is stochastic and so on. So, if you assume a model, you can generate as much data as you want. So that's one way of going. But there are other ways, like you can sort of collect some empirical data, and then there are ways of generating more data that is indistinguishable from, the empirical data that you've developed. So it's got the same sort of fat tails as the empirical data and that sort of thing. So there are, so either you can assume a model, or else you can, as I say, use a method for a machine learning method for generating as much data as you like that's indistinguishable from a relatively small amount of empirical data. So, but it is a big issue in finance, because we think we've got a lot of data in finance, but actually when it comes to machine learning, it doesn't go that far.
Finally, how do we solve the explainability problem?
Well, as I mentioned, there's a lot of work being done on this. Data scientists didn't care about how bad the black box was for a long time, but now they're under pressure to make their models more explainable. There's a couple of approaches that I'm familiar with. One is to it's actually known by the name of shapely values. It's basically saying, even if you've got some really obscure neural network model, one thing you can do is to say, well, what's the, let's suppose you're using this neural network model to work out the price of a house. You could say, well, what's the contribution of the number of bedrooms to this estimate of the price of the house? What's the contribution of the square footage of the living space? So what shapely values do is to come up with the contribution of each of the features, even if it's a really horrible nonlinear model, contribution of each of the features in such a way that the contributions add up to the total thing you're trying to forecast. So that's one way. Another way is to say, well, yeah, we've got this horrible nonlinear model that we don't understand, but we come up with a way of In the region we're interested in, as far as that model is concerned, we come up with a much simpler model that reflects the behavior in the region we're interested in. Maybe, you know, a relatively simple linear model or something like that. So you could say, well, if you regard some very complicated nonlinear model as being a whole series of linear models which are correct in different regions, then, you know, the model becomes a lot more understandable. So as I say, this is one of the areas where I think a lot of work is being done, and a lot of work will be done in the future.
Thank you very much, Mr. Hall. Great having you here again at the Risk Management Trading Conference.
My pleasure. Pleasure to be here.